Hi, so I wanted to do a couple of things. The first thing is that I want to show you um, how many in my project summary. I'm going to go look at a few different things. So to get to this project summary tab, you can click this button over here. And I can see a few different things. I have four warnings in my implementation, which I am going to ignore. My synthesis, I have no errors or warning. So recall that in order to generate the bit file, first I need to synthesize my design, and finally I output the synthesized design to my implementation, and the result of the implementation is what I use to generate the bid file. So I'm going to go look over here at utilization, and I can look at post synthesis or post implementation. Now, of course, post synthesis, the estimated utilization, or the utilization rather, is an estimate. Post implementation is my actual utilization. So I'm going to look here and I notice that I am using, let's look at it in table format. So I am using one LUT. So my entire design, everything uses one LUT out of a potential 20,800. So like something like 0.01%, right? Like I obviously I am capable of so much more complexity on my FPGA than what I'm using it for currently. And then for I/O, I'm using four I/O ports. So that makes sense, right? Because going back to my design, what am I using? I'm using three input switches, and one output LED. So those are my four I/O ports. And of course, notice that that matches what I have in my basis 3 master file. So I have my three ports, and scrolling down here, whoops, I overshot. I have my one LED. So where can I see all the I/O that I'm using? I can see it in three places. I saw it in my project summary over here. I saw it in my source, where I could see clearly that this module, it's the only module I'm using. It has three inputs and one output. And finally, I saw it in my Xilinx constraints file, design constraints file, rather. That's what the XDC stands for. So I'm going to go back and I want to show you a bit more of a streamlined way to implement my function. My Verilog code over here. You might be asking yourself, you might be saying, listen, you promised me that the whole benefit of using a hardware description language or hardware definition language is that I don't have to worry about gate level constructs. So I don't have to, basically what we did here is we derived the truth table for our module, which is a MUX in this case. Then using that truth table, we derived a Boolean expression, and then we implemented it we drew it as a gate level schematic. And then basically all we did is we kind of translated that gate level schematic into gate level Verilog. That's what this is called, is gate level Verilog. So this took me 5 lines of code for something so simple that it really only uses one LUT out of 20,800. So you might be asking yourself, like, is this really worth it? Like, what happens when I have much more complex designs? I'm still stuck, deriving the gate level specification for my design and then translating that into Verilog. I mean, what have I really gained by this? Is it so much easier? And the answer is no. You haven't really gained that much. It's not that much easier. It's a little bit of a pain. I mean, it's cool and everything, but surely there's got to be a better way. And there is a better way. And that better way is called behavioral specification. So we are going to distinguish that from gate level specification, which is what we did earlier and what's shown here. So right now, I am going to remove all this, these 5 lines of code, and I'm going to show you how I can easily implement them in a single line of code. So using behavioral specification. So what I'm going to do, and the rationale behind this, is I take basically the output y, and I assign it the value of this expression. So exactly what I have here, I am going to translate this statement into Verilog code. And the way to do that is I use the assign keyword. So again, I'm assigning to y. So the thing that I'm assigning to goes on the left-hand side, right? Just like a Boolean expression. I cannot assign to inputs. That doesn't make any sense. The inputs are given to me, but I can assign to my outputs. So I'm going to assign to y, so not s. In Verilog, that looks like this, not s. Oops. And so Vivado is trying to be smart by auto-completing for me, which is useful, but in this case, not what I want. I'm using the ampersand to denote and the second signal that I want to and is x0. And you know what I'm going to do, because this is a more complex expression. And so what I'm going to do, because just for the sake of clarity, although it's not really necessary, I'm going to put parentheses around each of these statements, just so that when I look it over later, it's very clear to me what are the operands for my OR operator. So the OR operator looks like this. And I'm going to open parentheses here and enter my second expression, which is s and x1. And I'm going to terminate my statement like I terminate all statements with a semicolon. Okay, and if I don't do that, that end module has the red wavy line under it. So let's look this over. First of all, every signal that I assign inside this statement, that I use inside this statement to assign to y, is already defined. And they're already defined up here. They're my inputs. What I'm assigning to is the output. Now, I have 3 different operators here. I have the tilde, which is a unary operator. I have the ampersand. So unary means that it only acts on a single operand, which is s. I have a binary operator, which acts on 2 operands, s and x0. And s and x1 over here. Sorry, not s and x0, and over here s and x1. And then I have the OR operator, which is that pipe symbol on your keyboard. I call it the pipe symbol, I guess, from sort of Linux terminology. So I'm not really sure what it's called, a bar. Anyway, I'm going to continue to call it a pipe. And on the left-hand side of the pipe, I have this expression over here, and on the right-hand side, I have this expression over here. So now it's very clear what I'm doing, and I'm going to go ahead and generate the bit stream, actually. So that will perform synthesis and implementation. If you want to see, so now this might be useful. Let's take a look at the RTL schematic. So one thing I wanted to show you is when I went to view the elaborated schematic, I can see that actually, even though I shrunk my code down from 5 lines to 1, I still have the same result. It ended up with the same RTL schematic. So that's the first thing I wanted to show you. Fine. Okay, so I've gone ahead and performed synthesis and implementation. And I'm going to go back and look at my project summary tab, and I'm going to look again at my post-synthesis and post-implementation tables. And again, really nothing has changed, right? I wouldn't expect, first of all, I would definitely not expect I/O to change. I'm still using the four ports, 3 input and 1 output. And I'm still only using one LUT. I mean, this is such a simple design, it can easily be implemented on a single LUT. So regardless of my specification method, whether I used gate level or behavioral specification, I'm still only using one LUT. So recall that this is an estimate because this is performed post-synthesis, but to obtain the actual number, I need to look at post-implementation, and the actual number for post-implementation is one LUT. So that is, I mean, that's pretty much what I expected. So regardless of the method I used, it is still using the same number of LUTs, which is one.